All right, I wanted to get into some of the technical details here of the semi-auto design. Just a brief overview. 4,500 psi fed through a regulator, comes out 1,800 psi into the valve. There's the hammer. And so where the complications start are the trigger and what differentiates a semi-automatic from a full automatic or single shot trigger. It was brought up in the comments yesterday and I just wanted to go over it. So bear with me here. Let's just pretend this is your sear and this is your trigger. And let's assume it's a Crossman 2240, for example, and you only need one shot, per cycle of the trigger. And nothing is necessarily resetting each time. So you pull the trigger, the sear disengages, the hammer goes forward, hits the valve, gas is released, fires the pellet. Done. When it goes back, it'll cycle and reset the spring-loaded sear, and you do it all over. For fully automatic, that could also work in theory. You pull the trigger, sear is disengaged from the hammer goes forward, a gaseous return fires it back, and then it can keep going until the user disengages their finger from the trigger and allows the sear to go back up. So whatever stroke that hammer's on catches the sear, and we've stopped firing. With semi-automatic, it's a different ball game, because let's say we have this same trigger and now it's a semi-automatic gun and we want to catch it and control it per round. So I pull the trigger, sear goes down, hammer goes forward, hits that gas for recoil, comes back. But guess what? That all happened in a couple milliseconds. My finger, I'm still pulling the trigger. And since I'm physically linked to the sear, it's not engaged. So the hammer goes again and fires again and again. So semi-automatic, you need to disengage the sear from the trigger somehow mechanically. Normally how that's done is this is angled and it's a wedge that catches the hammer up there, and it's spring-loaded. It's spring-loaded in this direction, let's say, about 45 degrees, 30 degrees. And it's spring-loaded upward, going that direction. So the hammer is pulled back and it catches this. So it catches the sear, and then that force overcomes the small spring on the sear. So it comes down to meet your trigger. So in the original position it was up here, and it cannot be interfered with by the trigger. Now the hammer is engaged on the sear and it comes down and it can meet. So we're starting from here and we're going to fire the gun. I pull the trigger, it tilts the sear enough for it to fire. Hammer goes forward and starts its path back. In the meantime, since this sear is not under pressure from the hammer, it can revert back to its original home because it's spring-loaded and be there in time to catch the hammer. Meanwhile, I might still be holding this trigger down, but it's not physically connected to the sear anymore because the sear has returned to its home position. So there's a slight disengagement where I can't catch it anymore. When the hammer catches the sear again, boom, it's jammed back down into the trigger engagement position. And for each shot, this same cycle needs to happen. It needs to be engaged, disengaged, engaged, disengaged for the system to work. But anyway, another thing I was looking at when I was dry firing, and I said to myself, well, this isn't going to be very powerful because these balls are big and heavy, and the steel slingshot ammo, and I'm not going to be pushing enough air because the system just isn't designed for a heavy hammer spring, because it would be harder to blow the hammer back, and it's all got to be synchronous with the amount of air coming back, pushing the hammer, the weight of the hammer, the friction in the hammer path, the friction of the bolt, which is actually riding on the hammer. It's going to be right here. So you have a friction problem and you have a weight problem for how much blowback you need to operate the system. And the hammer spring's a big factor in that blowback equation. But anyway, I looked at I ended up doing a bunch of math, even though common sense would have given me the answer. you know, the sectional density for the for like an 8 grain regular pellet would be something in the order of 2150 grain per square inch of profile, and the steel ball is only 1450. So it's you know, it's a significant difference in the sectional density. So we should be able to get decent velocities out of these. And you know, if you ever notice when calibers increase, let's say this was all set up for 177 and it was running 4500 psi and it was just a beast, and you're running 20 foot-pounds in 177, and then when you upgrade to, let's say, a 22 barrel, while the velocity may not be much different or might be slightly lower, the foot-pounds of energy goes up dramatically. And part of that, you know, can be calculated based on the chamber pressure or the pressure behind the pellet. So let's assume with the 177 pellet loaded, this valve, everything is optimized and perfect and it's 100% efficient. So your chamber pressure behind the pellet at the time of firing for a millisecond is actually 4000 psi. So the pressure on the rear of the pellet and on the bolt are both, let's say, 100 pounds of force based on the diameter of the rear of the pellet. You know, you can do the math: radius times pi times pressure. Let's say it's 100 pounds, and that's just a random number off the top of my head. Now, when you switch to a larger round, now take the 177 barrel and everything out of the equation, and now we put, let's make up a hypothetical, you know, 34 caliber, roughly double. We put a 34 caliber, and intuition would tell us, well, if we went from 1.7 to 34, you know, we should be at double the FPE. But then when we fire the gun, it's not. It's, you know, 3.5 times the foot-pounds of energy. And the reason is because when you take two different, you know, circle sizes, if the circle has doubled in diameter, it's quadratic. In other words, you've gone up fourfold in surface area. So instead of that 100 pounds acting on the 177 pellet, you know, you now have roughly 400 pounds of force acting on your 34 caliber pellet. And that's the reason the speed of the air and everything isn't going to change much, and that's why, you know, the velocity, you're still pushing more mass. That never changes, so the velocity may go down. But your force imparted on the round goes up at a factor of 4, which is not exponential. That's a different term completely. But it's quadratic, which is tricky, and it has a lot to do with the it's similar to the square cube law, if you ever heard that. Like if we doubled the size of a bumblebee, you know, it would be less efficient but able to fly. And then if we like tripled or quadrupled the size of a bumblebee, it wouldn't even be able to like walk around, or, you know, it wouldn't be able to fly at all. Like the wings would be too small. But anyway, back to the air gun. That's about it. I just wanted to cover some basics about how the trigger is going to be complicated, about how this round ball caliber will likely perform pretty well. The barrel's coming later today. I'm still not sure what I'm going to do with the trigger, whether or not I'm going to use a paintball trigger or just start designing and cutting from scratch. I'm probably running out of memory on this card right here. So more to come. Stay tuned.